Hello, my name is Anuj Bhatia, and this is my lab report for Physics 2211, Lab 1, Constant Velocity. So an introduction is in this lab, we rolled an expo marker on a table next to a meter stick and put the video into tracker, where we inputted starting time, ending time, mass, and distance. And we then made a computational model for this experiment in GlowScript and compared the results from both the tracker simulation and the computational model. And the purpose of this lab was to determine how constant velocity in ideal simulations, like the computational model, differ from real life, like the tracker where forces can impact the data. Some basic physics principles we used in this lab were Newton's second law and the velocity update formula. And after getting the results for this lab from both sources, we inputted the data into Excel to make position versus time graphs from both, which we will analyze later. And the graph for the computational model showed perfect linear motion as expected, but the graph for the results in tracker showed the motion to be slightly curved, which means that there is an acceleration or a net force, which we will get into later. Some equations we used were Newton's second law, F equals ma, which was used to analyze motion with constant velocity versus without, and the velocity update formula, which was used to update velocity for each increment of time. Some initial conditions for this experiment were that the system was the marker and the surroundings were the table or any other forces that might have acted on the marker. The initial mass of the marker was about 0.01 kilograms, initial time was 0.9 seconds, final time was 2.73 seconds, initial position was 0 meters in the x direction, and final position was 0.649 meters in the x direction. And the initial velocity was 0.350 meters per second, which was calculated using change in r over change in t. Some details about the actual tracker experiment can be seen here. And after the initial mass and time to start tracking were set, the marker is rolled and the software tracked the position of the marker in small time increments, which generated the position versus time graph in the top right and the data table on the bottom, which both were input into Excel and will be compared to the data from the computational model. So some details from the code or computational model are shown here. And the first part of the code initializes a graph, which shows a visualization of the marker as a sphere and how it moves. And the second part of the code creates a graph when the code is run, and which initializes the details like the title and the curve color of the graph. And the third part of the code initializes the mass of the marker, the initial position, initial velocity, initial time, and the increments of time that the graph will be simulated by. And most of this data is from the last slide, or last to last slide. And the further details about the code. So this part of the code creates a while loop for the time, starting time to the ending time and increments by delta t. And we input the initial velocity and then it updates the position and velocity and creates a curve for the graph where increments for every point of delta t and then prints it. So these are two graphs we made in Excel using the data from the tracker table and from the computational model. And as you can see, the tracker data is slightly more curved than the computational model, which is perfectly linear, which is to be expected because the tracker model likely had outside forces acting on it, while in the computational model, we assumed ideal conditions and constant velocity. So why there could be differences in the graphs, as I was saying, one of the main differences was probably because we didn't account for outside forces. And these forces could include things like friction or air resistance, which made the graph slightly curved, which means it had forces acting on it or an acceleration. And other sources of errors that might have caused the possible differences are things like software errors or calculation errors. So some additional questions that we were supposed to answer are what would happen if we flipped axes? And if I flip the axes, the graph would flip, so the slope would change signs, but the magnitudes of the values, such as velocity and acceleration, would stay the same. So none of the actual data or values in the results would change except for their signs, but that would still keep the same values and the same results that we are analyzing. And for the second question, about if we can predict the forces based on knowing that the net force is equal to zero, although we can have an idea of what forces act on the marker, like friction or air resistance, like I discussed, there's no actual way to determine what forces or how many forces cancel out to achieve net force. And in conclusion, the main conclusion that can be drawn from the results are that the data can vary from ideal simulations, such as a computational model and real life, because many of the assumptions in the computational model, such as constant velocity and no outside forces acting on the system, cannot hold true in real life. And the experiment showed relationships between constant velocity and forces causing acceleration through the differences in data and graphs. Thank you.